Okay, quick question from seminar sheet 3. What we're looking at in this case is, will these circuits work correctly? Will they bias correctly? What's actually happening inside this design? Okay, so let's have a look what we've got here. We have 120k as the base resistor and 10k as the collector load resistance. Okay, these are noted here and here. The beta value for this transistor is not what SPICE tell you. For this piece of maths, it's just a value of 60. And our supply voltage is 12 volts. So let's see how this circuit will work. If we have an equation for RC, okay, RC would normally be VCC minus VCE divided by IC, and for RB we would have in this case VCC minus VBE all divided by IB. Okay, we could write, of course, IB is equal to IC over beta if we chose to. Okay, so the question that you have to answer here is, will this circuit bias correctly? What are the values that we have for ICQ and VCEQ? So will this circuit work? So, big question, where do we start? We start here and we look at this bias line. Okay? So we've already got some numbers here, so it's quite straightforward to do. First off, we're going to use this equation here that we've already calculated. So we go RB is 120k equals 12 minus 0.7 all divided by IB. Okay, so those two can swap over. We can therefore calculate that IB equals 12 minus 0.7 all divided by 120k. 94 microamps. Okay, we should now just calculate IC equals IB times beta, which should give us, in this case, 94 microamps times 60 equals our value of collector current, 5.65 milliamps. Okay, so this is how this circuit should work. So we now know this current here, IC. So let's do a quick check. Let's now look at 10k. So VCEQ, our quiescent operating point up to here, should be equal to VCC minus ICRC. So that should be, let's just assume for maximum symmetrical swing 6 there, 12 minus 5.6 milli times 10k, and that equation doesn't work. Okay, if we look here, 5.6 milli times 10k is too great a voltage, 56.5 volts. So we end up with no way that circuit will balance to 12 volts. The circuit does not work. Therefore, this bias arrangement and these values are not suitable, certainly with a beta value of 60. So there's our sort of first design complete. Let's have a look at another design. This one's a little bit more complicated because we have a feedback bias. Collector resistance, base resistance. We're going to need to calculate out some values. So we've got our components on here. So we're working from 12 volt supply. It's not stated, but we're going to assume VBE, 0.7 volts again. So now we can calculate our equations for IC and of course for IB. This current up here, of course, must happen to be IE, if you'd notice, because down here we have the collector current plus the base current, and up here we have the collector current plus the base current. So we're working on IEs in effect here. So let's just write out one or two little equations. Okay, starting from the top, we can write out our our Kirchhoff's voltage, VCC minus Ooh, okay, yeah, sorry, VCC minus IE. Okay, so we're using the emitter current here as the current that's flowing at that point because we've spotted the difference, and then we multiply by RC. Then we add in, we then subtract VBE, and we would also subtract, in this case, IB RB, and all of that would equal 0. Okay, so if we want to relate all of that to, for example, the collector current, we could rewrite the expression VCC is equal to ICQ, okay, beta plus 1 over beta. So we're accounting for those fractions there, RC. We can add in this case, our base current, which is ICQ over beta, multiplied by RB, and we can also account for VBE. Okay, and there's our straightforward expression. If we now collect all of that on terms of ICQ, we can put all the component values in and just simply substitute. So let's just rewrite our expression for ICQ. Okay, so we can keep VCC on one side, we can keep VB on the other side. This is a term of ICQ, so does this. So doing everything in one step here. VCC minus VBE is on the numerator, and the denominator is made up from beta plus 1 over beta multiplied by RC plus RB also over beta. Okay, I personally just want to tidy that up by multiplying top and bottom by beta. It means we can cancel out these betas at the bottom here, make it look a little bit neater. We're going to end up with VCC minus VBE, okay, beta, all divided by beta plus 1 RC plus RB. Okay, and that just makes it a little bit easier. If we plug in all the numbers to that, we're going to calculate ICQ, our collector current in effect. We have 60 multiplied by 12 minus 0.7. Okay, and on the denominator we've got basically 61 beta plus 1 multiplied by 8.2 times 10 to the 3. Okay, that's this 8.2k, our collector resistance, plus then 800 times 10 to the 3, which is our base resistance here. Okay, if we plug all that lot together, we are operating at 561 microamps. Okay, that's the value that comes out for our collector resistance. Okay, if we plug, basically that's half a milliamp. Half a milliamp, we've got 12 volts here, we've got 8k, so that's basically going to drop about 4 volts. So roughly speaking, this is going to be around about 8 volts. Okay, therefore our conclusion can be the circuit works. Okay, please note to self as well, in the exam you may have some MCQs, you may be given a schematic diagram, you know, something like this. You might be given this, and the answer could be, you know, one of the answers could be, is this circuit working or not? Will it bias correctly or not? So it's a yes or no, and unfortunately you have to go through a little bit of maths just to work out whether it does or it does not work. You could also be asked for numerical values of the collector load current, okay, something like this. Again, that's why it takes you 2-3 minutes to actually work through one of those MCQ questions.